I will discuss the linear momentum equation. The linear momentum equation takes the form of Newton's second law for a fluid in a control volume that is non-deformable and coincident. The equation, in other words, is a time rate of change of the linear momentum in the control volume plus the net rate of flow of linear momentum through the control surface, and it equals the sum of external forces acting on the system. There are three terms a part of the linear momentum equation. The equation is made up of the fluid field velocity, density, volume of the fluid particle, and the mass flow rate of the control surface. There are a few simplifications to this equation. For example, the first term is always assumed to be zero due to steady flow. Also, we assume velocity is constant, and by the law of conservation of mass, which allows the second term to become m dot parentheses v out minus v in. Finally, we assume that the direction of the sum of external forces, which is the last term, must be the same as the velocity change. The final term is also a representation of the vector sum of all forces external to the control volume. For example, the gravity force, shear force, and pressure forces. When conservation of mass is assumed, the second term becomes an m dot term. The m dot term is negative for mass flow into the control volume and is positive for mass flow out of the control volume. This equation is best used for uniform 1D flow. It can be used to solve for forces acting on pipes with fluid flowing through them. To conclude, the linear momentum of a body is a product of their mass and velocity. In fluid mechanics, Newton's second law is usually referred to as a linear momentum equation.